All right, so recording from the school today, folks. I'll try and mute it really quickly if any announcements come on. But just a heads up, your ears might get blasted off a little bit if an announcement catches me by surprise. Now, today we are starting chapter 8. We'll explore some logarithmic functions. When we're doing so, in order to do so, first we need to remember how exponents work. Remember our work with exponents that we've done before. So first, we'll graph an exponential function, just our base exponential function. The base is 2. Our exponent is x. Nice and easy. We can do it by creating a table of values here. So if x equals -2, that means f at x equals 2 to the power of -2. Well, that equals 1 over 2 squared, and that equals 4. So f at x would equal equals 1 over 4. So f at x equals 1 over 4 if x equals -2. Now, we can then fill in the rest of our f at x values. You should be able to handle this pretty easily. This is all review. Now, if we put that onto a graph, nice and easy. Okay, so if x equals -2, then y equals 1 over 4. If x equals -1, y equals 1 over 2. If x equals 0, y equals 1. If x equals 1, y equals 2. And we can see this exponential function building here. Now we can sketch it in. We're expecting something like this here, where this base exponential function has a horizontal asymptote here at y equals 0. And nice and easily, we have an arrow at each end. It will obviously increase at an increasing rate as it goes on, so it gets steeper and steeper and steeper and steeper. If we were to zoom out here, it would almost look as if there's a vertical asymptote because of how quickly it increases, but there's not a vertical asymptote. There is no limitation in terms of the x values of an exponential function. So that is the domain of our exponential function is an unrestricted x is an element of the reals. The range of an exponential function, we can see right here, the range, we're only using positive y values. So y is an element of the reals such that y must be greater than just greater than, not equal to, because of our horizontal asymptote, greater than 0. Nice and easy. The asymptote we've already stated, y equals 0. Okay, now let's try and find the inverse of that function. Now remember, if we're coming up with an inverse, that's like a reflection over the line y equals x. And that is, and let's see here, yeah, we'll go with orange for our reflection line. That's a reflection over the line y equals x. If we're inverting a function, if we're inverting the points, that's like we're interchanging the y coordinates for the x coordinates and x coordinates for y coordinates. Right? So if we can use this table right here to come up with the values for x and y for the inverse, and that is we're coming up with the inverse function of x right here, then nice and easy, we just switch the x and y coordinates at every single step. So where x equals 1 over 4, y equals -2. Where x equals 1 over 2, y equals -1. Where x equals 1, y equals 0. Nice and easy. We're just interchanging all of these points. Okay, so now we can plot that here. Okay, so if x equals 1 over 4, y equals -2, we're looking at something like this. If x equals 1 over 2, y equals -1, okay. Sorry, x equals 1 over 2, yeah, y equals -1. If x equals 1, y equals 0. And we're seeing the shape be built here. If x equals 2, y equals 1. If x equals 4, y equals 2. Okay. So now we can expect. Now, since we had a horizontal asymptote at y equals 0, if we're taking the inverse, then we're going to need another asymptote. So right here, we can see the asymptote is coming into play at x equals 0. This time it's a vertical asymptote, not a horizontal asymptote. The general shape of our function, something like this, where it is increasing slower and slower as we go to higher and higher x values, but it is still increasing. The domain here, and sorry, because it's still increasing up to infinity if we want, our range is unrestricted. So y is an element of the reals. But our domain, we can see there are no values here on the left side of our vertical asymptote. So our domain, x is an element of the reals such that x must be greater than 0. And we notice the parallels that we discovered when we were first exploring inverse functions. Any restrictions that were on our range are now on our domain and vice versa. The asymptote already given is at x equals 0. Okay, fantastic. So how do the y values of the inverse relation relate to the base 2 and the corresponding x values? Well, these are all exponents that the base 2 must be raised by to get these x values, right? So we're remembering where this function comes from, this inverse function, where it comes from. F at x equals 2 to the power of x. Well, what we're plotting is the inverse of that. So we're plotting x equals 2 to the power of y, right? After we switch our x and y. Now let's see. So is this inverse a function? We can double check. We can zoom in this inverse function, this green that we've just drawn. Is this a function? Absolutely. It passes our vertical line test. So yes, this is a function. And I'll have uploaded with full explanations for these questions on the classroom by the time you're seeing this. Now we have already plotted the line of symmetry right here. We can see that this makes sense. Green is like a reflection over the line of symmetry from purple here. That is, the inverse function is a reflection over y equals x. That all makes sense. It lines up with our understanding. Well, this inverse function that we're finding, this is the logarithmic function, as we'll explore it here. Okay, so now let's try graphing. Now this, when we graphed this here, this is the general shape we can expect if our base, in this case our base equals 2. We'll expect this general shape if our base is greater than 1. Okay, if our base is greater than 1, then our function, our logarithmic function, is increasing. Our exponential function is increasing. And that is to say, if our base, whether it's our original function or its inverse function, if our base is greater than 1, then our functions are going to be increasing. All right, now let's move forward. What if our base is not greater than 1? Okay, so here we're working with g of x. And we'll go with, let's see here, we'll use the same colors. G of x equals 1/2 to the power of x. Well, nice and easy. Okay, so if g of x is 1/2 the power of x, then g of negative 2, then we're working with 1 over 2 to the exponent negative 2. Okay, well, 1 over 2 to the exponent negative 2, that's like 2 to the exponent positive 2. Well, that equals 4. Okay, so there's our first point, 4. G at negative 1 equals 2. G at 0 equals 1. G at 1 equals 1 over 2. And G at 2 equals 1 over 4. Okay, nice and easy. Now we can plot something like this. We can plot something like this very simply. Right, so we are working with right here, okay, we have the point negative 2, 4. Negative 2 up 4, nice and easy. Okay, negative 1, 2. 0, 1, 1/2, 2, 1/4. Okay, well, we can see right here that we're still going to be working with a horizontal asymptote at y equals 0. We can see that our function will go up towards positive infinity as x approaches negative infinity. Our general shape is going to look like this, where it's a general shape almost similar to if our function were reflected over the y-axis. I want you algebraically to maybe think about why that might be the case right there. Now, okay, so we have this general shape. Now we want, again, let's analyze that. The domain of g of x here, again, x is an element of the reals. Because this is an exponential function. An exponential function has the domain x is an element of the reals with no restriction. The range, okay, well, we are not using any negative values in terms of our y coordinates here. Whoops. In terms of our y coordinates here. So nice and easy. Y is an element of the reals, same as last time, such that y is greater than 0. Can it be equal to 0? No, there's a horizontal asymptote there. Our asymptote of g of x, as I listed already up above, y equals 0. Fantastic. Okay, then let's put it together once more. We can give ourselves that reflection line, our axis of symmetry between our function and its inverse, and then we can try and find the inverse points. Okay, well, here now where x equals 4, y will equal -2. Again, I'm interchanging these x and y coordinates. Where x equals 2, y equals -1. Where x equals 0, where x equals 1, y equals 0, where x equals 1 over 2, nice and easy, just interchanging all of these coordinates from up above, and then we can plot it. All right, well, where x equals 4, y equals -2, we're just putting it together right here, where x equals 2, y equals -1. All right. Nice and easy. And we can see here, because our original function crossed that axis of symmetry, we can expect our new function to cross that axis of symmetry as well. And we can see here the general shape being put together looks something like this. Well, this general shape, again, this has a vertical asymptote at x equals 0. So we can put that in where we know it exists. Okay, the domain, again, our restrictions we'll find will be interchanged from our domain to our range here as we look at the inverse function. Okay, so the domain of the inverse function, well, we're only using positive x values, okay? So x is an element of the reals such that x is greater than 0. Our range is unlimited. Y is an element of the reals. It goes up to positive infinity. It goes down to negative infinity. And we can see here the general shape. Okay, well, this time, both functions, the original function in purple, the inverse function in green, both functions are decreasing functions. And we notice that comes from our base being less than 1. Right? And you can algebraically, you can consider how that might happen. Okay, if our base is less than 1, every time our exponent increases, yes, our output will be getting smaller and smaller and smaller and smaller. All right, so there we are. We can remember that we're working with decreasing functions if the base is less than 1, increasing functions if our base is greater than 1. Okay, so we created the values. How did the y values? You know what? I will leave it to you to handle the problems like this. Whoops, we already did the last part to handle those problems. Try and explain those, and then we'll get into our key ideas. Okay, well, here what we are discovering right here is the logarithmic function. Okay, so this logarithmic function, the logarithmic function, is the inverse of an exponential function. Okay, this is what it's called the logarithmic function. You may have seen in your textbooks already, logarithmic function. You may have seen in your textbooks already somewhere where it says log base something of x, or just simply the log of x. Okay, so this is read the logarithm of x to base a. All right, the logarithm of x to base a. All right, the logarithm it is an exponent. It means that our exponent must be applied to this base to get to this value of x. Okay, so this right here, you'll probably want to highlight that right there. And if you are going into a summative and you think, hey, I might forget exactly how logarithms are built, you can copy exactly this down and you'll be able to understand what's going on. Now, we don't necessarily need to memorize this because we can consider, okay, well, log base 2 of 8 equals 3. Okay, so if we just write that down, we can think, okay, if it's base 2, then that means if I'm writing an exponent, my 2 needs to be the base, okay? And then I need something in the exponent right here, and that it will equal something. So if I work with these numbers, 2, 3, and 8, I can see right away 2 to the power of 3 equals 8. So I don't need to memorize this second part, but if you can remember the log base 2 equals 3, or as another log expression. If you can feel familiar with that, then you can piece together how it connects to an exponential equation, or an equation including an exponential. All right, now let's explore this a little bit further. So let's try and write the inverse of y equals 8 to the power of x in exponential and then logarithmic forms. Well, if we're finding the inverse, and you have done this a number of times already, if we're finding the inverse just like we did in the first chapter, the first thing we need to do is we need to switch, or we need to interchange x and y. Okay, well, if we're switching or we're interchanging x and y, then we're working with right here, and I'm going to write this using a few different colors, then we're going to be working with x equals, our base is 8 to the power of y. This is the inverse in exponential form. Well, we can write that into logarithmic form by setting it up. Okay, so we're working with here, we want isolated, we want our y, right? So y equals, and let's set it up with another color here. We'll just use black as a neutral color. Y equals the log, and then the base, well, what's the base? Base means the base from the exponent, right? It means the little piece under here that's getting multiplied by itself a given number of times in order to be evaluated. So our base is 8, so that is log base 8, and what's left? X. Okay, so y equals log base 8 of x. This is how we interchange into a logarithmic form. All right, now we should be able to then, we don't necessarily need to be, let me see here, I'll leave example 2, I'll leave that for you to try out on your own. You should be able to handle that. The only difference is that our base is now a fraction, right? And we're switching in the other direction. You know what, maybe I will handle this. We're switching in the other direction. Okay, so say then we're working with our base is 1 over 3. That's always where we start. We find our base. Our base is 1 over 3. Okay, so base of 1 over 3, and then I'm finding here, I'm seeing, okay, so x is on its own on this side of the equal sign, and then it goes into my logarithm, right? So if the x is on its own, then my x needs to stay on its own in this new equation. Okay, so 1 over 3 equals x, and what's my exponent? I need two parts. I need a base, I need an exponent, and what they're equal to. So in this case, what they're, my exponent down here was, whoops, over here was y. My exponent is in the same location there. 1 over 3 to the power of y equals x. Now, we should be writing this a little bit more carefully because really the base is 1 over 3. We should have brackets around that. Otherwise, it looks like only the 1 is to the exponent y, right? So we need to be a little bit careful. We need to take extra steps to be clear what we're writing when we're working with logarithms and when we're working with exponents. Now, example 3 is sort of a fun one when you get the hang of it. It can be a little bit, it might look a little bit intimidating to you off the start, but really it's pretty darn simple. Okay, so we're working nice and easy. Log base 16, sorry, we're working here. We see the base. Okay, so once we see the base, that's our hint. If we're switching it into logarithms, we know what to do with it. Log base 16. Okay, and now effectively these switch sides, right? It's log base 16 of 1 equals 0. Okay, well, let's try that again right here. What is my base? My base is 5. I see that right away. All right, so that means that we're working with right here log base 5, and then these switch sides of 25 equals 2. Same thing over here. You know what? I'll leave C and D to you to handle on your own. You should be able to handle those no problem. Again, the solutions are uploaded on the classroom already by the time you're watching this video. And lastly, I'll get to example 4 right here. We can evaluate these logarithms by putting them into exponential form. Okay, the tricks are all done once we have just done that first step, which is switching them to exponential form. So log base 4 of 16. Okay, well, I know that I'm working with base 4. All right, I know I'm working with base 4. I know the 16 needs to switch sides, if you will. So I'm evaluating 4 equals 16. 4 to the power of what equals 16? I'm not sure. That's an x. Okay, well, if 4 to the power of x equals 16, then I can rewrite both sides with the exponent 4. right? So this first step, I have changed it into exponential form. Exponential form. So whenever we're trying to evaluate a logarithm, switch it into exponential form and then try to work with it. Okay, 16. Well, I know 16 equals 4 squared. So that means 4 to the power of x equals 4 squared. So I can set the exponents equal to each other. Set the exponents equal. And then I'm working with, okay, x equals 2. Easy, finished, x equals 2, we're all done. Now let's get into the next one here, nice and simple. We're going to follow the same pattern. Okay, so log base 3 of 81. Well, the base is 3. The exponent, I don't know. The exponent equals x. And what does it equal? It equals 81. So now I need to find, okay, I need to be able to write this right side with the same base as the left side. All right, so 81. Okay, well, I know 81. I could do this in a couple of ways here. You might know 81 equals 3 to the power of 4. Or you might say 81 equals 9 squared. Right? And then I know how to break 9 down. So 9 is 3 squared times, or 3 squared. Right? So 9 is 3 squared. It's still being squared out here. We can use our exponent laws. All right, that means that 3x equals 3 to the power of 4. Well, now I can set the exponents equal. Nice and easy, x equals 4. All right, I want to see you try that same skill with C right here. And then D is a, you should be able to handle D as well. It uses one more exponents rule. So if you're getting stumped a little bit on D, then look up your exponent rules.